There's something weird out there in the universe. This woman made it famous. This man thinks he knows what it is, but he's never seen it. And this man isn't surprised, because he's convinced it doesn't exist at all. And that's a problem, because according to this man, it makes up 96% of the universe. Atoms are extremely versatile things. In various sizes and configurations, they make all kinds of stuff. Stuff like us, our coffee, our tennis rackets. Even children are made of atoms. Stuff made of atoms is everywhere. The sun, planets, galaxies, an entire universe of stuff made from atoms. Except there's a problem. It turns out that the entire universe isn't just made of atoms.
It's a very bizarre concept which is hard for us, I think, to conceptualize.
Something we can't see is pulling the strings of the cosmos.
It could be dust, it could be planets, or could it be some alien stuff?
The alien stuff, if it exists, needs to fill a very big hole, because 96% of our universe is unaccounted for. For some scientists, finding the missing 96% is the single biggest challenge in physics today.
Most of the universe is made of something else, and we have a chance to figure out what it is.
But for others, it is a search gone badly wrong.
It's not physics, okay? It's just there's fairies at the bottom of the garden.
The front line in the search for the missing universe is here, in the far north of England, at the bottom of a mine. Europe's deepest mine produces salt and potash, but these men aren't interested in all that. They're preparing to travel a mile into the Earth's crust to discover what's going on in space. They've been coming here for 16 years and have spent millions on scientific hardware. They're on the hunt for a brand new particle.
It's kind of surreal looking for a fundamental particle down a mine. Do you ever feel you're wasting your time?
Oh no, not at all, because the basic question that we're trying to explore by these experiments is so fundamental to physics and cosmology that one would go to almost any length to try and solve this puzzle.
But the business of uncovering the stuff of the missing universe can be a frustrating one.
The practicalities and the difficulties of doing these experiments and the care with which you have to do them, you know, dictate that things unfortunately do happen rather more slowly.
The stakes are enormous. If the problem is solved in the mine, the universe will be instantly understood, and Nobel Prizes will be thick on the ground. Unsurprisingly then, the world's deep mines are full of scientists looking for stuff with which to fill the universe. The hunt has been in full swing since the 1970s. By 1974, science was on a roll. It had conquered smallpox, invented space hoppers, and put men on the moon. What's more, science was happy with the state of the universe. It knew what the universe was made of, and none of it seemed to be missing at all. But then a pair of Princeton professors rather spoilt the party. In 1974, they were concerned with the tiny matter of trying to find out how much stuff there was in the entire universe.
Jerry Oestreicher brought to this enterprise a lot of astronomical knowledge that I didn't have. I was trained as a physicist. The astronomy I picked up in the streets.
What got Jim Peebles and I interested was work we had done the year before on the stability of galaxies.
In the early 1970s, Oestreicher and Peebles were doing pioneering work using computers to model the universe. But there was a problem. The virtual galaxies they tried to build simply fell apart.
We had discovered in trying to make a model for our own Milky Way that if you just put in the computer what you see in the sky, it doesn't work. If you make a disk of stars, it came apart in one rotation period and went into two blobs or a rotating bar or something.
The solution was simple. They just needed more stuff in their galaxies, because more stuff would provide more gravity, and more gravity would stop everything falling apart. In theory. The trouble was that in practice, there was no extra stuff to be found. So they invented some. They called it dark matter.
We had a problem. We have structures of galaxies that don't behave properly unless we introduce this new notion of dark matter.
Dark matter couldn't be seen and had never been detected. It was simply a name for the theoretical extra stuff that the simulations needed. But it wasn't a new idea. In the 1930s, when brilliant physicists were all the rage, one man, no, not him, one man, the brilliant but borderline psychopathic Fritz Zwicky, had noticed some actual weirdness. Not on paper, but in reality. It wasn't a theory. It was an observation, made with a telescope.
Fritz Zwicky was the first to realize that there was something up. He observed clusters of galaxies, and he saw them whizzing around one another, and the forces that were holding them together were not sufficient if you could only have in them the mass that was associated with the stars that you could see.
But Zwicky was a difficult man to get along with, so his scientific work had sometimes been overlooked. But his forgotten ideas about dark matter were a godsend for Oestreicher and Peebles.
We checked and checked our calculations, and then we looked back and saw Zwicky's work, who said that there was dark matter. And we put it together in the second paper, and it was all consistent with having almost 10 times more mass in dark matter than there is in ordinary matter, stars, planets, gas.
In 1974, Jerry Oestreicher and Jim Peebles announced to the world that galaxies just couldn't exist without dark matter. They needed loads of it, more dark matter than even the maverick Zwicky had predicted. The idea didn't go down very well.
People didn't like Zwicky, and they didn't tend to agree with his result, even though no one had any objection to it. And they didn't particularly like our result either.
I do recall a few discussions in which people said to me, you know, this is awfully speculative. And they were right.
The world was not yet ready for Jim Peebles and Jerry Oestreicher and their ideas about dark matter. But things were about to change, thanks to working mum Vera Rubin.
When I started working here, I looked for a problem that I could do at my own pace. I had 4 children and a supportive husband, but traveling was more difficult to go to observatories out west, which was necessary.
Vera decided to ignore the sexy science of black holes, which was very big at the time, and look instead at entire galaxies. By doing so, she stumbled across something much more fundamental. For 300 years, Newton's law of gravity has defined our understanding of the universe. Gravity governs everything, from falling apples to the ebb and flow of the tides. But to fully understand it, scientists have had to look beyond planet Earth. Gravity's mysterious power is clearest in the solar system, where the sun holds the orbiting planets in its gravitational grip.
If we plot the velocity of the planets as a function of distance from the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. And you can see that Mercury orbits much more rapidly than Pluto.
The graph is called a rotation curve. It is the embodiment of the law of gravity. The further away you travel from the sun, the weaker its gravitational force. Galaxies work in the same way as our solar system, except that instead of planets orbiting a central sun, in a spiral galaxy, stars are held in orbit by a gravity-providing black hole. In the 1970s, Vera's family-friendly project was looking for rotation curves in galaxies.
Невестная, иди